Part 4. How ancient light reaches us now. How does ancient light reach us? Let's recap. Once cosmic inflation ended, the Hubble surface was moving outward at nearly twice the speed of light, but with recession speed decreasing over time. Expansion was decelerating due to the energy density of radiation and matter. Expansion began accelerating when the matter energy density fell to twice the constant dark energy density. At that inflection, the Hubble surface recession velocity equaled the speed of light. Afterwards, it was less than the speed of light, and it will approach zero in the infinite future of exponential expansion, and the Hubble distance saturates at 5340 megaparsecs, assuming constant dark energy density. Prior to the inflection, galaxy recession velocities were decelerating, and a distant galaxy that had been receding at the speed of light will slow to sublight. It will cross inward into the Hubble sphere. Let's go back and look at the first stars again. Let's say that some of those stars constitute galaxy A. Earlier, I said that the light horizon distance now for light emitted by the first stars as early as 50 million years after the Big Bang is about 12,200 megaparsecs within our visible horizon. So this is the proper distance now to galaxy A. The Hubble distance is 4428 megaparsecs presently. The first star's horizon distance is much larger than our present Hubble distance and the cosmic event horizon. So any light emitted now, today, by galaxy A, whose early light we see today, will never reach us in future. The scale factor 50 million years after the Big Bang was 0.0206 and the redshift was 48. The proper distance between galaxy A and our position in the universe was 251 megaparsecs 50 million years after the Big Bang. The Hubble distance was 23.3 megaparsecs 50 million years after the Big Bang. The proper distance between galaxy A and our position in the universe was 10 times the Hubble distance 50 million years after the Big Bang, when starlight was emitted that we could now receive with redshift Z of 48. Galaxy A was receding from us at 10.7 times the speed of light at that time. So how did that light ever reach us with light only traveling at the speed of light? In general relativity, the path of a particle that always travels locally straight is called a geodesic, whether the spacetime is flat or curved and the universe is static or expanding. For photons of light and other massless particles always traveling at the speed of light, the path is called a null geodesic. This graph shows proper distance from us up to 2,000 megaparsecs versus time since the Big Bang up to 14 billion years. The blue square at the lower left is galaxy A, with proper distance from us of 251 megaparsecs, 50 million years after the Big Bang, whose light we are just seeing now. The purple curve is the Hubble distance, increasing with time. The black dotted curve is the proper distance from us of galaxy A, increasing with time and scale factor due to expansion. Galaxy A has always been outside our Hubble sphere and always will be. And yet we see its early light. It is within our visible universe, which is larger than our Hubble sphere. Light emitted from galaxy A toward us has always traveled toward us at the speed of light relative to local space, but the points in space were receding from us with the expansion of the universe. When the light was emitted by galaxy A was receding from us at 10.7 times the speed of light. After 1 year, the light wave front moved 9.7 light years further from us because the space where galaxy A is located moved 10.7 light years from us, and the light moved 1 light year closer to us through that space. It would be normal to conclude that this light will never reach us, but that is wrong. The proper distance from us of the light wavefront is increasing at first, but the co-moving distance, proper distance divided by scale factor, is reducing. With a little work, the proper distance from us of the light wavefront is the blue curve. At the left, the light wavefront is not keeping up with the position of galaxy A, drifting in the Hubble flow, but neither is it separating very fast, despite traveling at the speed of light. But follow the curve up and to the right, and over a few billion years, the light wavefront has separated quite a bit from galaxy A, even though the proper distance from us is still increasing. But at 4 billion years, the location of the light wavefront now coincides with the Hubble distance at the blue dot. The Hubble surface was moving outward at faster than the speed of light and overtook the light wavefront at a distance where space was receding from us at exactly the speed of light, and the light wavefront was traveling through space toward us at the speed of light. So briefly, the light wavefront was as far from us as it was going to get, and subsequently, its proper distance from us has decreased. And now it is reaching us. The blue diamond at the lower right. You may want to pause the video and check that you understand so far. The brown dashed curve is the recession speed from us of the point in space where the light wavefront is located at that time, with scale factor at the right, up to 10 times the speed of light. It started at 10.7 times the speed of light at the upper left. It passed through 1 times the speed of light at the brown dot at 4 billion years, when the blue curve was overtaken by the Hubble distance. And now it is 0 when the light reaches us, because space just outside our local group is not receding from us. So this starlight traveled for 13.72 billion years to reach us. For the first 4 billion years, the space it traveled through was receding from us at faster than the speed of light. For the subsequent 9.7 billion years, the space it traveled through was receding from us at slower than the speed of light. But the blue curve tells us more than just the light from the first stars. It is the curve of light reaching us now, emitted from any distant galaxy in the past. The red triangle is a galaxy with redshift z equals 10. The brown triangle is a galaxy with redshift z equals 2. The green triangle is a galaxy with redshift z equals 1. For starlight that we receive now with z greater than 1.6, emitted in the first 4 billion years, the emitting galaxy was beyond our Hubble surface at the time of emission, that is, receding faster than the speed of light, and yet the light has reached us. For starlight that we receive now with z equal 1.6, the galaxy was at our Hubble surface at the time of emission, receding at exactly the speed of light. This is the blue circle on the graph. This is the furthest proper distance from us at the time of emission for light that is reaching us now, 1780 megaparsecs. Galaxies with larger and smaller redshifts were closer to us at the time of emission. We can extend the blue curve to the origin to cover cosmic microwave background and early cosmic radiation. Though this section talked about starlight, it also applies to the CMB, gravitational waves, relativistic neutrinos, and cosmic rays. Radiation from some distant early galaxies, the CMB, and the early universe will continue to arrive at our location for our indefinite future, though at increased redshift over time.